How are we going to compute minimum edit distance? The standard algorithm is with dynamic programming. Dynamic programming is a tabular method of computation. And what we're going to do is we're going to compute d, the distance between two strings x and y, x of length n, y of length m, by combining solutions to subproblems. And combining solutions to subproblem is the intuition of all dynamic programming algorithms. The intuition is very simple. We're going to, for small prefixes of length I of string x and j of string y, we'll compute the distance between those strings, and we'll compute our larger distances for larger strings based on those previously computed smaller values. In other words, we're going to compute the distance ij between prefixes of string x of length I and prefixes of string y of length j for all I and j, and we'll end up in the end with the distance. So let's look at the actual equation. Here's the equation for defining minimum edit distance. And I've given you Levenshtein distance, which is the distance when there is a cost of 1 for insertions, 1 for deletions, and 2 for substitutions, excuse me. So let's look at the initialization condition. So we first say that any characters in x, so this is the x string, for the I characters in x string, the distance between those and the null string in y is the cost of deleting each of those characters. So the cost of those is the length of the string. We're deleting each character. And similarly, for inserting all the characters into y to create the string y, the distance between the null string of x and the string of y is just the length of y, the insertion cost of y. And then we'll do the recurrence relation. So walking through string x and walking through string y, we'll have that the distance in any particular cell of our matrix is going to be the minimum way of getting to that cell from 3 previous cells. If we go from the string I, that's one shorter, so we're deleting one more thing in I to make it j, or we're inserting one thing into j to make it longer, or we're substituting between the previous string I of length, x of length I minus 1 and y of length j minus 1, we're adding in a new character. If it's the same in both strings, we have a cost of 0. If it's different, we have a substitution cost of 2. And then at the end, the distance between the two strings is simply the d of nm, the upper right corner of the matrix. So here's our table, and we can fill in each element of the table from using this equation that tells us the deletion cost, the insertion cost, and the substitution cost. So let's do that. I put the equation up here in the corner. So we want to know what's the distance between the null string of intention and the null string of execution, obviously 0. The null string, the string I to the string nothing, is the cost of deleting an I, that's 1. So now let's try to compute what's the cost of converting in to e. Well, intuitively, we expect it's going to be a deletion and a substitution. So let's see if that works out. All right, so the element in this cell is the minimum of 3 values. It's this distance plus 1, this distance plus 1, or this distance plus either 2 if I and 0 are different, or 0 if they're the same. Well, they're different. So it's the minimum of I plus 1, which is 2, 1 plus 1, which is 2, or 0 plus 2, which is 2. So we have 2. So we're going to write 2 in this cell. Similarly, if we want to know the distance between in and e, it's the minimum distance of in to nothing plus 1, so 2 plus 1, or 3, or the different distance between I and e plus the cost of adding in that n, or 3, or the cost of having just an I and adding in that n to e substitution, which is 2, or 3. So again, we have 3 here. So we have a 2, and we have a 3. And if we continue along this manner, again, in each case, looking at the 3 previous cells and using this equation over here, we'll slowly end up with and so on. And if we continue along this in this manner, we're going to end up with the following complete table. So every cell in this table, let's take this cell, tells you the cost of the edit distance of editing the string INTE and turning it into the string EXE. And that means that this value here in the upper right corner is the cost, the edit distance between intention and execution, the cost of turning intention into execution. And we see the value 8, which we earlier said was the Levenshtein distance. So we have Levenshtein distance equals 8. So that's our algorithm for computing minimum edit distance.